So again, we're constructing our Lagrangian for this system, for this problem. Okay, mass little m is sliding down this incline, but it's sliding on a surface which is the surface of an object with mass big M, and big M may itself be moving in either direction. It will probably move backwards, and we're trying to determine what the motion is going to be for each of these two masses. Okay, so we have just two variables, x and x prime, which define these two, which define the positions, all the position coordinates that matter. Let me say that again. X and x primed are the only two position coordinates that matter here. Okay, if you know what x and x primed are, then you know everything there is to know about the positions of both masses. Okay, so we want to construct the Lagrangian. The Lagrangian has the kinetic and potential energy parts. We need to calculate the velocity in the inertial frame of reference. Okay, inertial frame in this case is just going to be, the frame of reference that we're looking at this system from. If we see this mass moving down and this mass moving to the left, big mass moving to the left, we're in an inertial frame of reference, and well, that's the frame of reference that we are considering here. Okay, so the velocity of big M is simply going to be, well, it just has the one component, so x dot is the x component of the velocity. Multiply that by I. And okay, here's the complicated one. The velocity of little mass is going to be the sum of two velocities. The first is the velocity of okay, maybe I'll do the second one. The second one is the velocity of little m with respect to the incline. In other words, with respect to big M. And the first term is the velocity of big M with respect to, well, the coordinate system in the inertial frame of reference. So that was just obviously big V. Okay? So again, what this means is, you can calculate the velocity of this mass relative to the triangle, but you have to add to that the velocity of the triangle in order to get the velocity of this mass little m with respect to this, well, for example, this wall here. So we're just adding two velocities in order to get the velocity of little m with respect to the inertial frame, with respect to this fixed wall, which is fixed in the inertial frame. Okay, there's another unit vector here, so I have unit vector I, which points in this direction. I primed is in the rotated coordinate system. It's directed along the incline, okay, in the direction of increasing x primed. Okay, so let's work with that. The kinetic energy is just going to be a half mv squared for the big mass, so that's v squared for the big mass is big V dot big V. So that's obviously going to be a half big M times x dot squared. That's easy. So that's a kinetic energy of big mass, or mass big M. Kinetic energy of mass little m is a half little m v squared. That's little v dot little v. But little v is this equation here. Okay, so we substitute that in for v and v. So we have two of these, two terms each. So it becomes what? Well, if we just expand with the dot products, first term will be x dot squared. We'll have second term with second term will give us x primed dot squared. And then we have two cross terms which are identical, which will be, when we sum them together, 2 x dot x primed dot, and then we have a dot product, not to be confused with the dot over the x, the dot of the dot product, we have I dot I primed. So two cross terms summed together, that's why we have the factor of 2. Now what is I dot I primed. Refer back to this figure here. This is I primed. What's the angle between these two? Well, if you do a little geometry, you can see that whatever this angle of the incline is, theta will be the same as the angle between I and I primed. Okay, I would point like this, and I prime points like this, so the angle between them would be the same as this angle, theta. So we use I dot I primed is equal to cos theta, because they're both unit vectors, of course. And there you go. Theta is not a variable. Theta is a fixed quantity, right? Remember, theta is just the angle of the incline. That's information you're given at the beginning of the problem. Okay. Now, what about the potential energy? Well, the potential energy is m times g times y. So that will simply be y is going to decrease as x primed increases. Okay, and if you do the geometry, so because y, the vertical position, decreases as x primed increases, that's why we have a negative sign here. And the relationship between y and x primed, well, they're not certainly not parallel with each other. They're not perpendicular. There's going to be a scaling factor, this trig function sine of theta. So you should be able to do the geometry to show that that's the relationship between y and x primed. And you can see why it should have a factor of sine theta. So I'll leave that as an exercise for you to do. It's just a little bit of geometry. Okay. Oh, and we're assuming here that y is equal to 0 when x primed is equal to 0. So we're choosing y equals 0 to be this level right up here. Y equals 0 is not down here. Y equals 0, we're choosing to be up here. It's totally arbitrary. Let's choose it here because it's more convenient if we do so. Okay, so here's the potential energy. The kinetic energy, remember, is two terms. It's this term plus the second term because we have two masses. The potential energy, we only have one term because the vertical position of the triangular mass is not changing. Only little m is changing its vertical position. So only one term for the potential energy. So here are the two terms for the kinetic energy. And then the potential energy, well, remember the Lagrangian is the kinetic energy minus the potential energy. The potential energy is negative. So minus the potential energy becomes positive mg x primed sine theta. Okay, we have the Lagrangian. Let's run with it. So the Euler-Lagrange equation for x and its time derivative looks like, whoops, there should be negative here, sorry. Where I have an equality here, that should be a negative sign. Correct that in your notes. Okay, time derivative of this derivative minus dl by dx equals 0. If you then look at this Lagrangian, dl by dx, let's see, I'm not sure I see an x anywhere. I see an x dot, I see an x prime dot, I see an x primed, I don't see an x. So actually this equation ends up being correct after all, because this is equal to 0. This term is going to necessarily be equal to 0. Okay, so try to follow the logic of that. Go write this with the negative sign for the proper Euler-Lagrange equation. Note that this term is equal to 0. Therefore, this term must be equal to 0. Therefore, the time derivative of, now you have to calculate the derivative of the Lagrangian with respect to x dot. There's an x dot, there's an x dot, there's an x dot. So there are three places where you see x dot. Okay, so take that derivative and then take the time derivative, and you end up with this. And we have x double dot and x prime double dot, and here's x double dot again. Those are essentially accelerations. Okay, now we'll do the same for the primed x and its time derivative. Remember, the dot means time derivative. Okay, so one way of writing the Euler-Lagrange equation is to put this on the other side where the 0 was, so it becomes positive. dl by dx primed, well, here's an x primed. And where else do we see an x prime? We don't see any other x primes here. All the other x's have dots on them. Here's an x primed. So the derivative of the Lagrangian with respect to x primed is just mg times sine theta. And the derivative with respect to x dot primed, or x prime dot, if you calculate it, it's this. So just go back up here, look for x primed dot. Here's one, here's another one. So there are two places. So there are two terms that show up in this derivative. Take the time derivative again, and you get this, this equation. So we have two equations that we've derived from the Euler-Lagrange equations, 4.71, 4.72. And I'm not going to take this problem much further. We have two basic unknowns in these equations, x double dot and x prime double dot. We have two equations and two unknowns, equation 71, 72. You can solve for this unknown, x double dot. Here you have it. You can solve for this unknown, x prime double dot. Here it is. The right-hand sides of both of these equations are all known quantities. So, and they're all constants. So the acceleration coordinate, x double dot, is equal to this, a constant. It depends on theta, it depends on both masses. Likewise, the acceleration coordinate for x primed might help to refer to the original picture here. The acceleration coordinate for x primed is also constant. Well, it's constant with respect to, the acceleration of this coordinate relative to a fixed point on this triangle. Okay, that is constant. All of this is constant. Now, the actual acceleration of this mass will be the sum of both of these accelerations. The acceleration of this mass in the lab fixed inertial frame of reference would be the sum of both of these accelerations. Anyway, that's as far as we're going to take the problem. You could then integrate each of these two equations with respect to time and get the position coordinates as a function of time. But I'm going to leave it here. Now, you could do this problem using standard Newtonian mechanics methods, but it's much more difficult. The Euler-Lagrange equation is a much more straightforward, as it turns out, a much more straightforward way of doing this problem. Okay, last thing to say. What's the usefulness of the Lagrangian formulation of classical mechanics? Well, for the problem that we just did, like I just said, it's often easier to analyze problems where we have systems with constraints. A constraint is one like here where little m is constrained to lie or move along the surface. Big M is constrained to move horizontally, so those are both constraints. Okay. It eliminates the need to describe mechanics using forces. You'll notice we didn't say anything about forces when we analyzed this problem. This formalism is also relevant for the development of advanced ideas in quantum mechanics, for example, quantum field theory. Believe it or not, it doesn't look like quantum mechanics has anything to do with this, but the formalism is relevant for the development of quantum field theory. So you're going to learn a lot more about Lagrangian and something called Hamiltonian, the Hamiltonian approach to mechanics in the advanced mechanics course. Okay, that's it.